to welcome back everyone to the last talk of day one of our workshop, and we are very excited to have David Gosset today to tell us about scattering theory, universal computation in relation to quantum walks. David, it's all yours.
Thank you so much for the introduction, and thank you and the organizers for putting on what has already been a very interesting meeting. So I'm going to speak about work that I did about 8 years ago with Andrew Childs and Zach Webb, but I'm going to try to put it in the context of other works that use the same techniques, and I'll try to speak about those techniques at the beginning because I think they may be of interest to those of you who work on continuous time quantum walks. Okay, so the techniques that I'm talking about are the relationship between continuous time quantum walk and scattering theory, which I think was already present in the first paper, as far as I know, by Farhi and Gutman in 1998 on continuous time quantum walks. So this sort of section has its origin in that paper, but was developed in subsequent papers, many of which I'll list at the end of this kind of part of the talk. Please do interrupt and ask questions. I can't see the chat presently, but just let me know if there are questions in the chat as well. Okay, so because we had already two talks speaking about quantum walks on graphs, this should be very easy. We're going to be talking about continuous time single particle quantum walk on a graph. So we have quantum walker, which you can think of as a particle that can be located at any vertex in the graph. And so the Hilbert space is spanned by basis vectors that are labeled by vertices of the graph. And the quantum walk is generated by a time-independent Hamiltonian that will denote H sub g, which is just the adjacency matrix of the graph. And an initial state psi of 0 in this Hilbert space evolves according to the Schrödinger equation, and since the Hamiltonian is time independent, the evolved state is just given by e to the minus I hgt acting on the initial state. Now, to kind of give a motivating example for the types of quantum walks where scattering theory is relevant, we can consider a quantum walk on an infinite path. So let's take our graph to be a path with vertices labeled by the integers. So the Hamiltonian is just the adjacency matrix of that graph. You could, if you like, think about this as being some kind of discretization of 3-particle in 1 dimension, sort of if you're familiar with examples that are studied, for example, in quantum mechanics. But that's a parenthetical remark, and it's not intended to make any kind of precise statement. Now, if you try to solve the eigenvalue equation, then what you will find is that the solutions are momentum states. So these are not, I've written their functional form here. These are not really states. You should think of them as functions that take, as input a vertex and output the complex number e to the minus ikx, because they're not normalizable. Another way to think of this is like the Fourier basis, right? The Fourier basis is not normalizable in the usual sense. But for every k in minus pi to pi, which we call the momentum, this k, you can define this momentum state as just a function that takes as input a vertex and outputs the amplitude e to the minus ikx. And formally they satisfy the eigenvalue equation. So the Hamiltonian acting on one of these momentum states gives you back 2 cosine k times the momentum state. And this is just all we've talked about right now are just this infinite path and it's sort of the solutions to the eigenvalue equation, which are kind of static things, right? We're talking about solutions to an eigenvalue equation, which you should think of as being like a static thing, because, for example, eigenstates don't change over time, under Hamiltonian evolution. But in this setting, actually, the eigenstates tell you about a dynamical process. And the connection is as follows. If I construct a wave packet, so in other words, if I take one of these momentum states and I truncate its support, So this is, I've written a functional form here. So if I take, e to the minus ikx for x from 1 to L and, normalize that state, then I get a wave packet which has support on these L vertices from 1 to L. And as L becomes large, I can kind of think of this as being some kind of like, approximation of the momentum state as L becomes large. But what you can show is that this wave packet will propagate with a certain speed, which is 2 sine k in absolute value. And moreover, well, okay, so here's a little video that that shows the support of this. This shows the probability of being at a given vertex over time if you start in a wave packet state. And of course, this thing propagates with speed, but it also, like, its shape changes. But in the limit of large L, kind of the, you can prove theorems about sort of how well the wave packet is approximated by just the initial wave packet, but shifted in space. So in some sense, like as L becomes large, you can show that the time evolution is really approximated by just propagating this initial wave packet in time with a speed 2 sine k. So the lesson here is that well, okay, maybe let's wait for the more complicated examples before we draw out some lessons. But that should be a fairly, I think, straightforward example of a quantum walk that involves these wave packets. But now we could consider a slightly more complicated example where we attach a finite graph g hat to 2 semi-infinite paths. So in other words, like g hat might have some finite number m of vertices. It doesn't really matter what g hat is for the purposes of this discussion. And we're going to choose 2 of those vertices of g hat, and we're going to attach semi-infinite paths to those 2 vertices. So those are the vertices that are shown here in white, or that have a clear center. And now we can imagine, like, on the very far left, preparing a wave packet and and then just letting it evolve in time under this quantum walk. So in other words, since this path is semi-infinite, we can just prepare this wave packet state way, way, way to the left. It doesn't really see g hat initially, and it will move with this speed 2 sine k towards the graph, and then you can ask what happens. And what will happen, and what you can prove, is that after some time, the wave packet will have scattered off of this obstacle. So it will come in, and then it will scatter. And the scattering process there's sort of 2 things that can happen. And because it's quantum mechanical, these 2 things happen in superposition. There will be, at some late time after scattering has occurred, there will be a transmitted wave packet moving with momentum k on the right, and there will be some reflected wave packet moving with momentum k to the left, and the transmission will occur with some amplitude t of k that maybe we don't know. T of k can depend on details of the graph g hat, and the reflection again will also occur with some amplitude r of k that also depends on details of the graph g hat. So here's a little video that shows you an example of this. You can see that there's a reflected and a transmitted component of the probability after some time. And you could also, this was all considering the situation where you take the wave packet initial state on the far left, but you could also define a scattering process where we start on the right and send it moving leftward towards the graph. And for that process, we could also have potentially different transmission and reflection coefficients. So for this situation where we have a finite graph attached to 2 semi-infinite paths, there are 4 relevant scattering coefficients: transmission and reflection from the left, and the corresponding ones from the right. And again, here, the point that I want to emphasize is that the reflection and transmission coefficients, they describe this dynamical process of like actually preparing a wave packet and scattering it off of the graph, which is something that happens as a function of.
Can I ask a question?
Yes, please go ahead.
Yeah, I didn't understand why there would be a reflection. I would suggest that the incident wave packet will just choose either of the two paths, the graph, the upper one or the lower one, and then go and be transmitted. Means what's causing this reflection?
Why is there a reflection is the question?
Yes. Means I can understand a tunnel barrier or some impurity or some other defect was there, and then there could be a reflection. But here there is nothing.
Well, there's not nothing. So this graph G hat is is not described here explicitly, because everything that I'm saying will work for any finite graph G hat that you attach. So you could imagine situations where transmission occurs and reflection coefficient is 0. But there are also scenarios in which, in fact, generically what will happen if you choose, for example, a random graph G hat of some finite size, you're going to find that there is a non-trivial transmission and reflection coefficient. So, I think that the analogy with the continuum only goes so far, and I'm not sure if that's what's informing your question, but certainly I can assure you that if you select some, I mean, we'll see some examples later where the transmission does occur with unit probability, but generically that there can also be a reflection with non-trivial amplitude. I don't know if that helps.
Means then the reflection is only because of the G hat. Means I would suppose.
Oh yes,
that
that's right. Yeah, in the
other,
absence of G hat, you just transmit. I mean, the case that we considered before of just the line with no obstacle.
Yeah.
That case, perfect transmission. That's right.
Okay, thanks.
Mm-hmm. Okay, so the point that I was making here and that I want to emphasize is that, the reflection and transmission coefficients, they describe this dynamical process that happens as a function of time. Like things are changing, you're scattering, but to actually define, like, how do you compute the reflection and transmission coefficients? Again, it's going to be, they're defined, and the way you compute them is through static objects, which are, again, eigenstates of the Hamiltonian that are not normalizable. Okay, so to do that, it's going to be convenient to label the vertices on the paths. So we can label the path on the left, path 1, and the path on the right, path 2. And then going out from the graph, we're going to label the vertices by positive integers, 1, 2, 3, and so on. And so what do I mean by the scattering states? Well, in this situation, there's 2 scattering states for every momentum, one that comes in from the left and one coming in from the right. The scattering state will label SC1 of K is the one that comes in from the left. And it is the solution to the following set of equations. So the first 2 equations here, they describe the scattering state on the semi-infinite paths, the left path and the right path. So this first equation, it says that on the left path, there should be a component that is incoming with momentum K, and a component that is reflected with reflection coefficient R1 of K. Here the subscript 1 is because this is the scattering state with subscript 1. This amplitude on the right path has only the transmitted coefficient with outgoing with momentum K. And I've also written the eigenvalue equation here. The reason I've written it is because that determines the amplitude of the scattering state at all vertices in G hat that are not on the semi-infinite paths. So we should also constrain, just by the functional form I've written here, the scattering state will satisfy the eigenvalue equation with eigenvalue 2 cosine K at every vertex on the semi-infinite paths except possibly this one. And so then this last equation ensures that it also is satisfied at all of the other vertices of G hat. So we can just solve this set of equations for T1 of K, R1 of K, and the amplitudes of the scattering state inside G hat. And there is always a solution. And we can do the same for the scattering state that is incoming on path 2 from the right. And again, now there will be a different transmission coefficient, will denote T2 of K, a different reflection coefficient will denote R2 of K, and that's kind of the story for this kind of scattering process.
So a question, David?
Yeah, please go ahead, Ash.
So from where did you derive these equations? I mean, is this a general form for any, does this allow for any kind of scattering, or depending on what T2 and R2 and the T1 R1 are, or is it specific to these eigenstates like e to the ik that you started with?
Yeah, so this is the general scattering scenario for a finite graph with two paths attached. Now, you could so you can consider any finite graph G hat, and there will be scattering states, SC1, SC2 of K. There could also be bound or normalizable eigenstates of this Hamiltonian, and one can show that the bound states and the scattering states together form a complete basis for the Hilbert space, complete orthonormal basis. But and one can also show, to unpack your question, I think.
I guess the question would then be, why are there only, a few of these basis states in these expressions that you've written?
Oh,
right.
So like here, this determines the scattering state on the left semi-infinite path. So this is for every x, every positive integer x. This second equation determines the scattering state on every vertex on the right semi-infinite path, because again, x is a positive integer, and now this 2 labels the path on the right. And then this eigenvalue.
Sorry, if I may interrupt. I guess the question is, why is momentum preserved?
Why is momentum preserved? Well, maybe I can just say the following thing, which I think is the safest answer, which is that I think your question about why is momentum preserved is a question about why is there a solution to these equations for every k?
And why does it represent the most general solution?
Yeah, so there's a solution for every k because this set of equations can be shown to have a solution just because it's, I'm going to, on the next slide, or a few slides from now, I'll give you a matrix equation for all of these coefficients, and it's sort of just a set of linear equations that always has a solution. So, that you can see kind of algebraically. Now, why are there not other scattering states that correspond to k changing after it comes out, for example? So after transmission, why is k the same as it came in? Maybe the safest answer to that is that, again, you can show that if you define these scattering states for every momentum, first of all, you can show they exist because there's a solution to these equations. Second of all, you can show that these, along with the normalizable eigenstates of the Hamiltonian, form a complete basis for the Hilbert space. So those are sort of all the eigenstates you get. I think that a more physicsy answer would be that, momentum is conserved, but I'm not really sure exactly how to argue that in this discrete scenario. Does that make sense?
Yes, thanks.
Okay. Right, so we have these SC1 of k, which is, and SC2 of k, which are the scattering states. These are unnormalizable eigenstates, or you should think of them as functions from vertices to complex numbers. And for every k, we can define these things. And one thing I didn't say here is that, I kind of indicated on the previous slides that one can prove that these dynamical processes, like where you have a wave packet prepared on the left of some finite size, L, you can show that as L becomes large, these R of k and T of k really do describe the reflection and transmission of that dynamical scattering process. So in other words, the reflection and transmission coefficients that we can define through these static objects, the scattering states, really do define what happens when a wave packet is scattered, if the wave packet has a large support. Okay, but the S matrix for this scenario where we have two semi-infinite paths attached to a finite graph would be just the 2 by 2 matrix that contains the 4 coefficients R1 of k, R2 of k, T1 of k, and T2 of k. And it turns out that this S matrix is unitary, and this is not hard to prove, for every momentum k. It's a unitary matrix. And that's not surprising because, well, if you believe what I said about this describing the scattering process in the limit of large wave packets, it should be unitary because that is a unitary time evolution that we're describing. Okay. Now, this was kind of specific to this scenario where we have a finite graph and like 2 semi-infinite paths attached, but one can generalize it to a scenario where we have n semi-infinite paths attached to n chosen vertices of a finite graph G hat. And in that scenario, you can imagine preparing a wave packet on any one of the paths coming into the graph with momentum k. And so, and then after scattering, the wave packet will be in a state which is moving outward on a superposition of all of these paths with certain amplitudes. And so in this case, the S matrix that describes all of those scattering coefficients is an n by n unitary matrix for every momentum k. And one can prove that this S matrix, which I will give you a formula for on the next slide, it not only is it, are these coefficients that appear in some kind of eigenvalue equation, they also actually do describe a dynamical scattering process where a large wave packet moves towards the graph and then subsequently scatters. So I did want to include in this talk just like the formula for the S matrix, because I think it's kind of a beautiful formula. I'm not sure what else we're supposed to get out of this slide, but I thought I would put it here because it's very simple. So let's suppose we write, we have this finite graph G hat, and we're choosing n of the vertices of G hat to connect to semi-infinite paths. And then G hat can also have like internal vertices that are not connected directly to the semi-infinite paths. So let's just write G hat as a block matrix where this, these vertices are the ones connected to the paths. So this is an n by n block A. And then this D are all the, this block describes the connections between all the internal vertices. And then of course, B describes the connections between the internal and the external vertices, okay? So this is just the adjacency matrix of G hat written in this block form. Then it's convenient to define a matrix function gamma of Z. So here Z is a complex number, and it just has the following form. It's again this block matrix with blocks of the same size as in the previous line, but now we have, instead of A, B dagger, B, and D, we have this funny deformed thing with Z's appearing. And then the prescription for computing the S matrix in this general scenario is the following. You should construct this gamma at with argument e to the ik, and then invert it, and then multiply that by gamma of e to the minus ik, and put a minus sign in front. And if you do that, you get, again, a block matrix, and you should look at the top left block, which is n by n. And that top left block will be the S matrix at momentum k. Now, it could be that there are issues with inverting gamma, and then you can sort of take a limit as you approach the desired value of k. Okay. So this is the sort of simple formula for the S matrix, and it shows you that it's sort of easy and efficient to compute the S matrix given a graph G hat and a selection of vertices where you're going to connect these semi-infinite paths. Okay, yeah, please go ahead.
How did you calculate this gamma?
Oh, yeah, I didn't derive this formula, certainly in the talk. So this formula appears, for example, in my paper with Andrew Childs from 2012 called Levinson's Theorem for Graphs 2, where we describe some of the details of this discrete version of scattering theory. But it's this is not particularly hard to derive this formula, but yeah, I didn't do it here. Okay. So yeah, I mean, I think it's sort of, it's clear that if I give you a graph, you can compute the S matrix. What's certainly not clear is, like, suppose you want to have some graph that achieves a desired kind of scattering behavior. How do you design a graph that does what you want? Where the S, if I give you an S matrix, can you give me a graph? I mean, that is a more challenging problem, and certainly that's the sort of problem that is relevant to the kinds of applications that we usually care about, right? Because we want to perform some kind of quantum computation, or we want to transform states in a certain way. And if you want to use this technique, then you should understand how do you design a graph that transforms states in the way that you want, or has the desired S matrix. And I'll describe a little bit more in detail later in the talk. But I do want to discuss some of the sort of famous applications of this discrete version of scattering theory that appear in the literature. And one of them is, the famous paper that Ashwin spoke about in the previous talk, the exponential speedup or the glued trees problem using quantum walk. And Ashwin was mostly discussing some other aspects of that problem, but the quantum walk algorithm, if you consider a quantum walk on this glued trees graph that Ashwin had in his talk, which I have not shown here, the quantum walk has a kind of symmetry, and if you impose that symmetry, or you sort of like start in the, if you start in the entrance vertex and evolve with the quantum walk, then you only ever explore a very small subspace of the Hilbert space, and one can show that the time evolution is equivalent to a quantum walk on a line with weight. So here is a path of length 2n plus 1, and all the weights on the edges are 1, which is kind of normal for a quantum walk, except the one in the middle, where this corresponds to where the cycle that Ashwin was talking about occurs. There's a weight of √2. So you can consider this to be like, in the limit of large n, you can consider this to be, essentially, you have this obstacle, which is this edge of weight √2, and you have, very long paths attached on either side in the limit of large n. And so to understand the eigenstates of this quantum walk Hamiltonian, one can use this discrete version of scattering theory. A second example, which was the first paper I ever read in quantum computing about 14, 15 years ago, very beautiful paper by Farhi, Goldstone, and Gutman, who showed, who gave an optimal quantum walk algorithm to evaluate a certain type of Boolean formula known as a NAND tree. It's not really important what the formula is. The setting is that you have an input, which is you can query bits of the input, but you want to compute some specific function of the input, which is this NAND tree function, and the output of that function is either 0 or 1. And Farhi, Goldstone, and Gutman showed that you could design a graph, which sort of, this is a picture from the paper, but this picture describes the kind of graph that they look like, or that they consider, where you have this kind of like obstacle in the middle, and you attach very long paths, they call them runways, on the left and right. And then the obstacle is designed so that if you prepare a wave packet on the left and send it towards the graph with a very specific choice of momentum, then if the output of the NAND tree function is 0, the wave packet will reflect. And if the output is 1, then the wave packet will transmit. So the whole thing is designed so that the scattering off of this obstacle at a certain momentum evaluates the function for you that you care about. And the remarkable thing about this application is that they showed that this algorithm was optimal in terms of the number of queries to this oracle in this kind of query setting that Ashwin was describing earlier. And this was the first quantum algorithm that achieved the optimal runtime for that, or the optimal query complexity for that problem. This is not really an application, but I did want to mention that Andrew Childs and DJ Strauss wrote a paper about Levinson's theorem, and with Andrew, I generalized that that theorem to this setting that I described earlier, where you have many semi-infinite paths that are connected to a graph. And Levinson's theorem is a theorem in scattering theory that relates a certain kind of, well, in this setting, what it does is it considers the determinant of the S matrix. The S matrix is unitary, so its determinant is a complex number, like of unit magnitude. And you can consider, like, how many times does that complex number wind around the unit circle in the complex plane as the momentum k ranges from -π to π. And that is the winding number of the determinant of the S matrix. And the remarkable thing is that that winding number actually counts the number of normalizable eigenstates of the Hamiltonian, and that's Levinson's theorem. And it's a kind of remarkable connection between the scattering states, or the S matrix, and the bound or normalizable eigenstates of the Hamiltonian. But I would not, even though I put it in this list, it's not really an application, I would say, of this scattering theorem. Finally, and perhaps most relevantly for this talk, Andrew Childs in 2008 showed that you can perform any quantum circuit by a single particle quantum walk on a graph. And with Andrew and Zach Webb in 2013, we showed that you can also do this with many particles on a graph, but you know, our construction with many particles, in fact, a linear number of particles in the number of qubits, you know, uses a graph of much smaller size. And I'll describe these results in the rest of the talk. So at this point, if there's any questions about the sort of scattering theory or the history of this, now would be a good time, because I'm going to switch to describing kind of these last two results in the rest of the talk. Okay. So, universal quantum computing. So in this first, I want to first describe how you can perform a single qubit unitary by quantum walk. And this is sort of the basis, or the first step towards Child's universality result for single particle quantum walk. So first of all, we want to perform a single qubit quantum computation. So we need a way to encode a qubit in a quantum Walker state. And so the way that, or one way to do that is to you know, have a graph with sort of two long paths, one on the top, one on the bottom. And you know, if the particle is on the top, we can say that's the encoded zero state. And you know, maybe we want to be more specific and say that not only should it be on the top, it should be in some specific kind of wave packet, like a wave packet with a specific value of the momentum. And in Childs' work, that momentum is chosen to be π/4, kind of for technical reasons. So the encoded zero state is a particle moving with momentum π/4 on the top rail of this sort of dual rail encoding. And if the particle is in a momentum π/4 wave packet moving on the bottom rail, that would be the encoded 1 state. Now, let's say we want to perform a single qubit unitary. So now we can have like some kind of graph G hat, which is a finite graph, and we have like the zero, like a long path connected on the left, corresponding to input state, you know, corresponding to the input computational basis state 0, and a long path on the left corresponding to the input computational basis state 1. And we have the same kind of long path on the right for 0 and long path on the right for 1. Now imagine that we could find a graph G hat. Like, let's say we want to implement a single qubit unitary U. So this is a 2x2 unitary matrix. Suppose we could find a graph G hat where the S matrix at the momentum we care about, which in this case is π/4, has the following block form. So here we have like a 2x2 block that is all zeros here. What that means is that if you come in on the left with momentum π/4, no matter where you are, on the top or bottom or superposition of both, this block tells you that you don't reflect backwards. None of your amplitude reflects backwards. It all goes to the output paths. So that's good, because we want to sort of, you know, we want things to move forward in this picture, right? That you have a wave packet coming in on the left, on the top or bottom, or a superposition of both. we want, after scattering, the wave packet to be moving to the right on these paths on the right-hand side. And moreover, this U tells you that not only are you moving to the right on the output paths, but the unitary U has been applied within this, in other words, like the amplitude on, the amplitude on 0 and amplitude on 1 are described by this unitary U. So we've applied that U to the encoded qubit. So this is kind of like the desired situation, right? Given U, we want to find a graph with this S matrix of this form. So how do you do that? Well, Childs showed that the following two graphs implement single qubit gates of the following form: a phase gate that's written here and a basis changing gate that's written here. And these two unitaries, these 2x2 matrices, they are a universal set of 1 qubit gates. And what that means is that if you give me any other 2x2 unitary matrix, I can give you a sequence of these unitaries that approximates it. So you give me the unitary and some desired precision, and I will give you a sequence of U phase and U basis gates that approximates the unitary you want to within that precision. So, given, and in the scattering picture, you can do the same thing. So if you take these graphs and, connect them together, then you'll get a graph that implements the product of these unitaries. And so in this way, you can design a graph G-hat that implements, up to a good approximation, any unitary that you like on a single qubit encoded in this way.
Sorry, this pi/4 is universal for any graph?
Sorry, I maybe don't quite understand the question. So the pi/4 is, yeah, go ahead.
For any graph, if I have a momentum pi/4, I will get this kind of block of diagonal S matrix.
So the statement here is that if you take these two graphs, this one and this one, and connect them together, and take any sequence of these and connect them together in series, you will always end up with a graph with an S matrix of this form. And moreover, the U that appears in this bottom left will be the product of the U's that that appeared in the sequence of graphs that you showed. So that there are some special things that are happening here. Like, it's not always true that S matrices have this form when they have 4 semi-infinite paths, but these things are kind of designed to be tuned in this way, so that we have this nice. So
it's for specific graphs. So it's for specific graphs.
Yes, that's right. Mm-hmm.
Yeah.
Okay. So it's not hard to see that you can generalize this idea to simulate an n-qubit quantum circuit by single particle quantum walk. And this is what was done in Child's paper in 2009. And this, maybe it helps to kind of draw this picture, because really what you're trying to do there is you're trying to construct a graph G-hat, which has 2 to the n input paths and 2 to the n output paths. And each of these input paths and each of these output paths corresponds to like a basis vector in your n-qubit Hilbert space. And you want to design this graph G-hat so that its S matrix implements, a given quantum circuit on n qubits. And that is what Child showed how to do. And actually, it might sound much more complicated, but it's not so much more complicated than these pictures. It's just that you also have to think about how to do a 2-qubit gate. And that involves kind of like, well, that's kind of the reason why you need to have, well, maybe I won't say too much more about that, but I will say that it's not much more complicated than what I just showed you. But the main conceptual point I want to make here is that, the graph here has size which is at least exponential in n, right? Because you have to have at least 2 to the n input vertices and 2 to the n output vertices, each corresponding to a basis vector of your n-qubit Hilbert space. And that's really a requirement, because a single particle quantum walk, if you want to simulate a quantum computation in a Hilbert space of dimension 2 to the n, it doesn't really make sense to say that you could do it in a Hilbert space of smaller dimension, or at least we certainly don't think that should be possible. But in this work in 2013 with Andrew and Zach Webb, we showed that you could perform an n-qubit quantum computation using a linear number of quantum particles. So now, instead of just a single quantum walker, we now have like n. And the graph, the benefit of adding a linear number of walkers is that the graph now can be reduced in size from exponential to polynomial in n. And so that's what I want to tell you about in the remainder. So how do we do that? Well, first I better tell you kind of what the model of multi-particle quantum walk is that we consider. So just like before, we have a graph, and let's say that we have distinguishable particles. Then the Hilbert space would just, we would have a basis vector for every, we would just record the locations of these particles. So we would have particles 1 up to m, and we would say, particle 1 is located at vertex I1, particle 2 is located at vertex I2, and so on. It's going to be important for us to also consider indistinguishable particles. And in that case, you can't say like particle 1 is here and particle 2 is there, because the particles are themselves indistinguishable. So in that case, we would, but you can still sort of describe the states of such particles in this Hilbert space I just wrote down. So bosons would live in the symmetric subspace of this Hilbert space. So any symmetric state would be a bosonic state. And fermions would be like a state that is antisymmetric under permutations of the particles. Now, the Hamiltonian for
David,
go ahead.
this is a question from a few slides ago, where you were describing graphs which implement, desired unitary operators. The question is, how do you invert that expression that you had for, the S matrix in terms of the adjacency matrix of the gadget?
This one.
So how do you get this adjacency matrix of G hat out of the last equation that you have?
Yeah, so I mean, there's no direct way to do it. And for these universal gates, a set of single qubit gates, I think it was just done by a numerical search over small graphs to find ones that implement universal set of single qubit gates. But once you have that, then you can use universality and the fact that these things compose to build, to build graphs that implement any unitary up to a given precision. So there's not a prescription for finding a graph that implements a desired unitary. There was also, I should mention, a paper that I'll cite later on by Bloomer and others who sort of cataloged many unitaries and graphs that implement them up to 9 or 8 or 9 vertices or something like that. So I think the tools are basically numerical search for small graphs and then some kind of compositions using the way that S matrices compose.
Thank you.
Okay, so we're going to consider, actually for the purposes of this talk, it's going to be most relevant to think about indistinguishable particles, and you'll see why later, although we do show in our paper how to perform universal quantum computation using distinguishable particles as well. The Hamiltonians will consider, we have like you can think of the first term here as being an independent single particle quantum walk for each particle, but that's not going to be enough to perform universal quantum computation, perhaps unsurprisingly, because if you have non-interacting particles, you can just simulate their evolution by just considering them separately. And so we're going to have to add an interaction between the particles. And, for the purposes of this talk, you can just think about that as being nearest neighbor interactions. So some kind of energy penalty when the particles are close to one another, like next to one another in the graph. Or you could consider, for example, a penalty if 2 particles are at the same place, if they're bosons, for example. But you're going to see later in the talk, and there's sort of an intuitive reason why our results work for almost any interaction type that you choose, as long as it is local with respect to the graph. So that is the model of multi-particle quantum walk that we consider. And this captures, all sorts of many-body interacting systems in physics, although, of course, here we're considering them defined on more general graphs, like graphs that wouldn't necessarily appear naturally in physical systems. So how do you simulate a quantum computation by a quantum walk? And here, as I said, I'm going to focus on a multi-particle quantum walk of indistinguishable particles for reasons that will become clear. Well, again, we're going to just encode each qubit using a particle that moves as a wave packet. And, we have an encoding where we have two long paths, and a particle moving on the top is encoded 0, and on the bottom is encoded 1. And, but we're going to do this for each qubit, right? So now we have n qubits, and we're going to, so like on the left, we'll have like 2n input paths instead of 2 to the n, right? And for single qubit gates, we're going to keep the particles far apart, and we'll make them scatter from these kind of subgraphs like the ones I showed you earlier that implement single qubit gates. And the tricky thing is, how do you do a 2-qubit gate? Like, it's kind of easy to see that if the thing I showed you earlier, which demonstrates how to implement a single qubit gate, you can just do that on n qubits independently and construct n single qubit unitaries in tensor product, if you like. But the tricky thing is, how do you do a 2-qubit gate? And for that, we really need to use the fact that, well, for that, we need to understand some kind of 2-particle scattering. And that is what I'm going to describe in the following. I guess there are some like kind of technical things that we do that I'm going to describe first, which are kind of, well, it'll be helpful to understand the whole thing if I just describe it in sequence. So we do rewrite the circuit using single qubit gates and this special 2-qubit gate, the CP gate, which is just 1s and then a -1 in the last position. And we rewrite the whole quantum circuit to be simulated using the following circuit identity. And it's not really important that you parse this. What is important is that this CP gate can be implemented using a sequence of gates that involves a special mediator qubit. So like the CP gate, it acts between these 2 qubits at the top. These are like our data or computational qubits. But all the 2-qubit gates in this expression on the right-hand side act between one of those qubits and this special mediator qubit. And the only single qubit gates we need on the mediator qubit are Hadamard's. Okay, so we're going to add this extra mediator qubit, and it's going to make our lives a little bit easier. So the circuit, when we transform it in that way, we have n computational qubits, those are the ones we had initially in our quantum circuit. And then we have this 1 mediator qubit. And we have to show how to implement single qubit gates on all the computational qubits, only Hadamard gates on this mediator qubit. And we also need to show how to do this CP gate between the mediator and a computational qubit. So we never have to do a CP gate between 2 data qubits or 2 computational qubits. Okay, so like I said before, we're going to encode these qubits using wave packets. And so like if we had 3 qubits here, one of which is the mediator, we have now 6 paths because we have a top and bottom rail for each qubit. And these data qubits get encoded with wave packets moving with momentum pi/4, just like in Andrew Childs' scheme. But this mediator qubit gets encoded with a different momentum pi/2. Okay, and that we'll see the reason why that is. Okay, so then for 1 qubit gates, again, we can just use these graphs like from Andrew Childs' construction to implement 1 qubit gates because the particles are all separated and there's essentially no interactions going on when they're separated. I mean, this is a cartoon picture, and of course we prove things rigorously in our paper, but I think hopefully this helps you understand what's going on. So for single qubit gates, we can just use these gadgets from Andrew Childs' paper and momentum pi/4. At momentum pi/2, there is a Hadamard gate, which we found in this Bloomer et al. Paper, which cataloged many gates that can be implemented using small graphs. So this is the graph that implements Hadamard at pi/2. Okay, so then the tricky thing is, how do you implement this controlled phase gate using a graph? And so like this graph, yeah, it's going to have 4 input paths and 4 output paths. And it should be that when you have these particles coming in with momentum pi/4 and pi/2, encoding 2 logical qubits, the mediator and the data qubit, the output should, first of all, it should come out in the same encoding it went in it. Like the fact that it preserves the encoding, is not a given. And so like first of all, we want this scattering process of these two particles in this graph to preserve this encoding. But second of all, we wanted to implement this gate. And that is kind of tricky. And I want to tell you about how that works. So we use kind of the simplest fact about two-particle scattering to make this work. And I haven't actually talked to you at all about two-particle scattering, but here goes. So I want you to imagine a scattering process where we have a particle with momentum pi/4 or some momentum. It doesn't matter that it's pi/4 and pi/2 here, but let's say we have a particle moving from the left with some momentum, in this case pi/4, particle moving from the right with momentum pi/2, and that's at t = 0. So what happens at some later time? Like after this, presumably they go towards one another, and then after some time, there's some final state where the particles are moving outwards, away from one another, and you can ask yourself, what are the possible things that can happen here? And Ashwin, to your point earlier about conservation of momentum, if you were a physicist, you would say we have two conserved quantities here. One is energy and one is momentum. And because energy and momentum are conserved, there should only be one possible final state, which is the particle that came in, we should have a particle moving to the left with momentum pi/2 and a particle moving to the right with momentum pi/4 at late times. There's not, because we have two conserved quantities, energy and momentum. And so it should, if these were distinguishable particles, they could reflect or they could transmit. But because they're indistinguishable, there's no distinction between the situation where they reflect and their momenta are exchanged and the situation where they transmit through one another. And so for indistinguishable particles, you can argue this based on physics intuition, or you can actually prove this, that there is only one possible final state, which corresponds to this particle moving to the left with momentum pi/2, this one moving to the right with momentum pi/4. And then you can say, well, what is the effect of the interaction in this process? Because we said that we're going to be talking about multi-particle quantum walks, and you can choose whatever interaction you like that's local. And the effect of the interaction is to add a two-particle scattering phase to the global phase of the wave function is determined by the interaction. So everything I'm saying here, you can understand it in terms of there is a two-particle scattering state of this Hamiltonian that describes the scattering process, just like we had single particle scattering states that describe dynamical scattering processes in the earlier part of the talk.
David, there is a question on the chat.
Okay.
From Alistair.
Okay. Oh, I've got it here. So do the gate sections induce time delays on the wave packets? If so, does this make it awkward to choreograph the arrivals of both wave packets to each 2-qubit gate? The answer is yes and yes. So, when you say awkward, it's awkward in the sense that it took me probably hours to get it right in our paper and make sure that all the lengths were lined up. And yeah, if you look at the appendices of our paper, we have, you have to get the lengths of every section right. And we go to great lengths to be very specific about that in our paper. But yes, it does matter that things are choreographed. But you can do it. Okay, but getting back to this two-particle scattering, yeah.
Sorry. So maybe we will go another few minutes, and maybe end about 3:30 or something. Is that okay?
Oh, I'm sorry. How long have we been? I've been going for way too long, haven't I? Oh, excuse me. Okay, well, I apologize. I think I can wrap up very, very quickly. So let me do that. Yeah, the details of the interaction determine this two-particle scattering phase. And then essentially what we show is that, Right. So what we show is that you can design a graph that routes these two particles towards one another only if both qubits are in the encoded logical state 1. So in other words, that's the situation which corresponds to this bottom right matrix element of this 2-qubit unitary that we want to implement. In all other cases, the two particles don't get routed towards one another, and so we have this just identity occurring in the logical encoding. Okay, and then you know, this C theta gate, you can choose an integer so that it approximates the CP gate that we want. And how we do that is using another gadget, and I don't know, there's this whole cartoon picture that shows. So there's this gadget that routes these particles according to their momenta, and you can sort of understand, you know, based on the encoded input states, that they only get routed onto this very long path in the middle if they're both in the encoded state 1. Okay, so I think I should end there, but the point is that you know, there's also an error bound which which describes how big these wave packets need to be in order to implement a circuit of n qubits with the desired precision. And we do a lot of work to rigorously prove that wave packets of large enough size are sufficient to achieve the desired precision in the final output state of computation. Okay, and we also give some extensions and refinements of our scheme. And I apologize for going over time. I lost track of the time in the middle of the talk. And thanks for being here and asking all those interesting questions. Thanks.
Thanks, David. Let's thank David for the talk. Are there any other questions?
I have a question. Unfortunately, it's about the less interesting part of your talk at the start. So we're just looking at the situation, simplest case, you've got a graph with two infinite tails.
Mm-hmm.
What is your Hilbert space?
Yeah, I mean, so you have a countable set of basis vectors, one for every vertex of this graph. Now, does that satisfy you, or?
I'm not sure that space is complete.
Yeah, I mean, I think so. In our
sure
paper, yeah. So in our paper, the thing is that ultimately we're only interested in. So okay, I can give you my excuse for doing things this way, which is that
I'm not really trying to get you to justify yourself. I'm just trying to understand it, so you don't need to think of it as an excuse.
Well, no, but I think it is delicate because ultimately we're interested in the case where the paths are truncated, and so.
Well, that's a second can of worms, which I'll ask about in a second. But go on.
Yeah, I mean, I guess for the infinite case, I think about this, the vector space with basis vectors, one for each vertex of this graph. But it may be that there are subtleties that we have not accounted for there.
Well, yeah, that's not what I'm sort of. Yeah, I guess I'm just hoping for a more concrete description. I mean, since you brought it up, I'm a bit uneasy about saying that finite paths can be are approximations to an infinite path. Mm-hmm. If you're looking at starting at, say, the left-hand end of a finite path, mm-hmm. that's only a good approximation of the infinite path for a limited range of times. After a while,
yeah. So in our paper, so I mean, the way we deal with this is that in our 2013 paper, we proved theorems that show, if you compute the S matrix in the way that we prescribe using this, infinite situation, we have a formula. And so if you compute the S matrix using that formula, then what we show is that if you have, instead of the infinite graph, you have a finite graph with long paths, and we tell you how long you have to take them. And if you prepare a wave packet of length L, and then we give an approximation to the time evolved state, which tracks the wave packet moving towards the graph, reflecting with the given amplitudes, and then we give an error of the approximation time evolved state that depends on L and the length path.
Yeah, that sounds fair enough. Yeah. Thanks. And thanks for an interesting talk.
Thank you.
Any other questions for David? Okay, if not, let's thank David again. Thanks, David.